Hi everyone, we are back and we are going to do some fitting and regression analysis and looking at R squared and R values and all of those good things and confidence bands. So let's read in some important libraries. Let's do tidyverse. We're also going to read in library, ggplot2. Let's read in library NLME, nonlinear model fit. All right, so let's go ahead and let's look at MT cars. This is a data set that looks at cars, and we can look at cylinders, displacement, HP, MPG, all of that good stuff. So let's take a look at plotting some of this data set. Let's do ggplot. Let's do MT cars. Let's do AES. Let's say X equals horsepower, and we want to look at horsepower versus Y, my miles per gallon. And let's do plus geom point plot. And let's look at our plot here. And actually, we'll kind of blow this up a little bit. So we have our data set. Looks like an interesting curve. So let's say I want to apply and just do a linear plot just to visualize. So I can do plus geom smooth, and I can get a fit that is basically, it is applying essentially this method of least squares, and we're setting up and applying basically the best. It's just trying to fit this function based on minimize essentially the difference between those data sets. And then you're looking at the 95% confidence interval right here. So we can specify in geom smooth. So instead of just doing a fit, we can just specify a method. So the method we can specify as basically LM, which is a linear fit. So now we can set that same data set up to this point here. So we can plot it with our confidence interval, these bands, or we can plot it method and standard error. We could each issue that as false. So you just plot the line itself if you are interested in doing so. We can also say, if I want the, I can set my level, actually here, I can set level equal to 0.95, and you'd see the 95% confidence interval. If I do 0.999999, we should see it get smaller. Oops, excuse me. 99% of the, excuse me, that should be getting bigger. If it's 0.8, it should be very small. So 80% of our data, 99% of our data, 95, et cetera, et cetera, et cetera. So you can see that those bands changing. So it's a cool way to kind of show your data set in a different way. Now, let's say I wanted to get some information about that fit. So I can do lin model, and I'm going to do LM, which is my method. So I need to set, my formula is going to be equal to MPG, so my Y, as a function of X, HP, and then my data is going to be equal to MT cars. And I do that, I can do my summary of my lin model, and I can get some of those values. So I can see my intercept, my HP, standard error values, so you can see from those fits. If I want the coefficients, I can get my coefficients of my lin model here, and you can see that they match. So my y-intercept, my slope, which is negative, which makes sense because we're looking at something that is negative. You can see t values and p values for, again, based on those fitting parameters per se. Excuse me. You can see your multiple R squared. So you can see an adjusted R squared value. Excuse me. So regression analysis, you can see F statistics and P values as well. So this gives you a pretty good readout in terms of in terms of some of those variables and some of those fitting parameters. So that is something that's pretty nice to get out of that. We could also look at R. Let's see if we get R correlation function. Let's do. So let's see. You can can look at the correlation coefficient. Let's look at core. So you could calculate some of those values as well as examples. So we can go ahead and see, you can look at a lot of different correlation coefficients as well. But you can calculate those in R and fitting for the function, but this is giving you a nice output for this. You could also look at different types of fitting models as well. So for example, let's go back to our plots. Let's say I want to do model poly 2. And I want to set this as, again, linear model, even though it's a basically second order polynomial. So I can do formula. Again, I'm going to say MPG, again, my y-axis. And then now I'm going to look at poly, my polynomial function. My x-axis is, again, my HP, and then second order. And then finally, data MT cars. I can do my summary as well. So, summary of model poly 2. And we can see, and if we can look at the coefficients as well, coefficients of model poly 2. I have my same coefficients. You can see t-values, errors, p-values. We can see our multiple r squared, as well as the adjusted, and a lot of those values. So again, first order, second order, negative because, as we'll see in just a second, and we can go ahead and actually plot that too. So I'm going to copy this. Let's go ahead. I'm going to copy this. I'm going to go and say my method. I'm also going to specify, let's just do 0.95. And I'm also going to say formula equals, and I'm just going to say poly, and I can just specify x2. Oops. Formula. Let me see what is happening here. Actually, let's get rid of the level. Oops, I need to, excuse me. Let's undo. Let's delete this. Poly, it does not like that. Excuse me. Formula, I need to specify my y. My mistake there, and x of 2. So, and we could also do the same thing here where we can do level equals 0.8, for example. And we can see, oops, we need a comma. And we can see the shifting there. So this is really nice. And again, but we could also go back up here to the linear model. And if we wanted to, we could actually calculate core, and then we can specify some of our values here. So we can do the correlation of our variables. So if we take our data MT cars and we include let's correlate MPG. Let's make sure. Actually, let's do X and Y. So let's do HP. And empty cars include, again, let's actually teach that function. So let's look at this function. Not that. Let's see how we do. So we can see extract or replace parts of an object. So we're just extracting essentially values here. So you can kind of see how we could utilize this. Where is it? The elements of Y named A. So we're just basically pulling out those elements. So empty cars, and let's do MPG. Let's go back to our plots. So we can correlate those values. And we see a negative correlation, which makes sense when we're looking at the relative correlation between those values. Fantastic. So, but let's say I wanted to do something a little bit more exotic per se. Let's say I wanted to look at, let's go ahead at the beginning here. Oops, let's go ahead. Let's say I want to do something a little bit different. Let's say I want to look at a nonlinear fit. So let's say I'm going to do my nonlinear fit, and I am going to set this as NLS is my function that's going to do nonlinear least squares. So we're still going to do a regression analysis even on a nonlinear fit. So we're going to do MPG as our Y value, and it is going to be correlated to A, our fitting parameter, times 1 plus X, which is our HP, to the B power. Now, we have to set our data, as we've done before, so empty cars, and we also have to start and give it one of the, and this is kind of a limitation of R, to be honest, in regards compared to Mathematica, you want to start it with some values for it to search. So it's not going to automatically do it. So we want to set some values to start looking at, and then iterate and regress. You can set like the number of regressions and iterations. So sometimes it may have difficulties finding it. So you're going to have to kind of finesse that a little bit. So let's do summary of our NL fit. And we can see some of our values and p-values as well. So you can tell you something about the fit. You notice that we have residual error, and we have t-values and p-values, but we don't, and it tells you the number of iterations to convergence, and it gives you the tolerance, but we don't have necessarily our R-squared values for that nonlinear fit. So coefficient, coefficient of NL fit, again, will be the same. So with our values, we can now start to plot our nonlinear fit too. So what we can do is we can insert into this GM smooth. We have to define our method. So our method is going to be equal to NLS, nonlinear. Our formula is going to be our function, so y a times 1 plus x to the b, and then let's go ahead and set, actually we'll set later, method r, method, dot args, method dot args, and that'll be equal to list and then start, list start equals, list start equals, and then another list. A, let's just start it at 200. Even though we know the coefficients below here are 280, let's just start at 200. Let's start B at -1 per se. And then we'll go ahead and do comma SE equals false. And you can see, actually we can see the function here, different function here, but we can see our function right here. This is our nonlinear fit. Cool. So we're fitting it. Now we can't do with this function the 95% band, the width and the confidence interval in R easily. We're gonna have to look at other functions to do to perform that. But we have this nonlinear fit. So this is regression analysis, and this is fitting in R in a nutshell. So we'll see you all in the next video, and in the next, actually, work hard on your projects, and we'll see you all in the next class. Thanks. Bye.